In this lesson, you will learn about advanced routing concepts that are relevant to enterprise networks. After completing this lesson, you will have the practical skills and knowledge required to describe how FortiGate routes traffic, diagnose routing problems caused by reverse path forwarding check, identify sessions that will be routed through a different path after a routing table change, and using debug commands to troubleshoot routing and WAN link load balancing problems. This section covers general routing concepts and troubleshooting. FortiGate is a stateful device, so it decodes a lot of information at the beginning of a session based on the first packets. For any traffic session, FortiGate usually performs only two routing lookups. One on the first packet sent by the originator, and another one on the first reply packet coming from the responder. After that, all the routing information is written in the FortiGate session table. However, after a change to the routing table, the route information is flushed from the affected entries in the session table. So, FortiGate would perform additional routing table lookups in order to repopulate the session table with the new routing information. How does FortiGate decide routes? FortiGate has multiple routing modules. The diagram shown in this slide illustrates the logic of the routing modules. First, FortiGate searches its policy routes. You can view them using the command diagnose firewall proute list. If there is a match in a policy route and the action is forward traffic, FortiGate routes the packet accordingly. If the action is stop policy routing, FortiGate goes to the next table, which is the route cache. You can view that content using the CLI command diagnose IP rtcache list. Finally, FortiGate searches the forwarding information base, FIB. The FIB is generated by the routing process and is the table used for packet forwarding. Think of the routing table's purpose as management, while the FIB's purpose is forwarding. This separation becomes clearer in FortiGate active-active HA. In an HA cluster, both route management and forwarding tables exist on the master FortiGate. But on the slave FortiGate, only the FIB exists. If there is no match in any of those tables, FortiGate drops the packet because it is unroutable. When there is more than one route to a destination, this is the process for selecting which route to use. First, FortiGate uses the most specific route, which is the one with the longest net mask, or smallest subnet. If there are two or more routes with the same longest net mask, the unit selects the one with the shortest distance. After that, the lowest metric is used as the tiebreaker for dynamic routes. In the case of static routes, the priority is used instead. If there are multiple routes with the same net mask, distance, metric, and priority, FortiGate shares the traffic among all of them. This is called Equal Cost Multipath, ECMP. ECMP is supported for static, BGP, and OSPF routes. FortiGate adds a static route to the routing table only if all these requirements are met. The outgoing interface is up. There is no other route to the same destination with a shorter distance. The link health monitor, if configured, is up. The next hop IP address is in the same subnet as one of the IP addresses assigned to the outgoing interface. Let's review an important routing concept: reverse path forwarding, RPF check. RPF check protects against IP spoofing attacks and routing loops by checking the route to the source IP address. This check is performed on the originating packet only, not on reply packets. This check is performed only before the session is created or after the routing table is changed. If the check fails, the packet is dropped and the debug flow shows this error: reverse path check fail drop. There are two RPF check modes: loose and strict. Loose is the default mode. In the loose mode, the packet is accepted as long as there is one active route to the source IP through the incoming interface. It does not have to be the best route, just an active one. In the example shown in this slide, the packet from 10.4.0.1 to 10.1.0.1 is accepted because FortiGate has an active route, the default route, to 10.4.0.1 through port 2. However, the packet from 172.16.1.1 to 10.1.0.1 is not accepted because there is no active route to the IP address 172.16.1.1 through port 3. In strict mode, FortiGate checks that the best route to the source IP address is through the incoming interface. The route not only has to be active, as in the case of loose mode, but it also has to be the best. If you use the same example, but change FortiGate from loose mode to strict mode, you will get the following results. The packet from 172.16.1.1 to 10.1.0.1 is still blocked because there is no route to the source IP address through port 3. The packet from 10.4.0.1 to 10.1.0.1 is also blocked. There is an active route to 10.4.0.1 through port 2, but it is not the best route to the source IP address. The best route to 10.4.0.1 is through port 3. So, strict mode accepts traffic from the subnet 10.4.0.0/24 only when port 3 is the incoming interface. Content inspection requires symmetric routing. That is, traffic must follow the same path both ways. So FortiGate routes traffic symmetrically. This means that, under some network topologies, FortiGate might not route the return traffic through the best path, but through the same path that the originating traffic used. For that purpose, FortiGate remembers the interface to source and uses that interface to route the return packets, even when a better route using a different interface exists. Let's take a look at an example in the next slides. Let's analyze this network topology. The local network 10.1.0.0/24 has 3 network devices: a local workstation, a local router, and a FortiGate, port 1. Also, FortiGate port 2 is directly connected to the local router, using the subnet 10.2.0.0/24. There is a remote router connected to FortiGate port 3, and behind that, a remote server, 10.4.0.1. So any traffic destined to the remote server must be routed through FortiGate. One important detail in this network is that the local workstation default gateway is 10.1.0.254. This means that if you send an ICMP echo request from the local workstation to the remote server, the packet goes to the local router first, then to FortiGate, then to the remote router, and finally to the destination. When the ICMP packet arrives to FortiGate, an entry for the originating traffic is created in the unit route cache. This entry contains the interface to source, or the incoming interface where the packet arrived, which in this case is port 2. Additionally, FortiGate creates an entry in the session table. This entry also contains information about the interface to source. As explained earlier, FortiGate does a first routing lookup to find the next hop to the destination. That IP address is also stored in the session information. As there is not an ICMP echo reply yet, you will notice that the next hop to source is still undetermined. It is 0.0.0.0. It will be determined with the second routing lookup that happens with the first reply packet. Now, let's take a look at how FortiGate routes the return packet. When FortiGate receives the ICMP echo reply, because there is already a session and a route cache created, it uses the interface to source. So in this case, the unit routes the packet through port 2 towards the local router, even when there is a better route to the destination 10.1.0.1. The FortiGate routing table shows port 1 as the best route to 10.1.0.1, which is locally connected, but it still uses port 2. The objective is to keep the traffic flow symmetric. With the first ICMP echo reply, the second entry is added to the route cache, this time for the return traffic. Additionally, the unit does a second routing lookup, this time to find the next hop or gateway to the source. That IP address is added to the session, where 0.0.0.0 was before. What happens if the traffic originates from the server side instead? Let's say that the ping is sent from the remote server to the local workstation. In this case, when the ICMP echo request arrives at FortiGate, there is no session yet. So the unit uses the best route to 10.1.0.1, which is through port 1. This example shows how a FortiGate might, in some network topologies, route packets to the same destination differently, depending on who initiated the session. Let's take a look at the reply traffic in this example. Because the local workstation default gateway is 10.1.0.254, the ICMP echo reply goes to the local router first. Then the packet arrives at FortiGate port 2. The result is asymmetric routing. The return traffic is following a different path than the originating traffic. The return packet is arriving at port 2 instead of port 1, where the originating traffic was sent. In these cases, FortiGate accepts this asymmetry. No packets are dropped, and UTM inspection is not affected. When FortiGate is not applying source NAT, SNAT, after a change in the routing table, the routing information is removed from the sessions that are affected by the change. Additionally, related route cache entries are deleted. So, 2 more routing lookups are done for the next packets in order to learn the new routing information and store it in the routing table. Also, RFP check is done again for the first packet in the original direction. This slide shows a sample of a session just after a routing change. The gateways in both directions change to 0.0.0.0/0, and the interface is to 0, indicating that this information must be learned again. Additionally, the dirty flag is added. In sessions where SNAT is applied, the action that FortiGate takes after a routing change depends on the SNAT route change setting. When this setting is enabled, the action is the same as it is for sessions without SNAT. Namely, routing information is flushed from the session table. Route cache entries are removed. Routing lookups are done again for the next packets. This can potentially change the outbound interface being used to route the traffic, and RPF check is done again for the first packet in the original direction. When the SNAT route change setting is disabled, the behavior that occurs after the routing changes is different for sessions using SNAT. Sessions using SNAT keep using the same outbound interface, as long as the old route is still active. In the example shown in this slide, FortiGate is connected to two different ISPs. A client with the IP address 10.1.0.1/24 is connected behind a FortiGate. The FortiGate is doing SNAT of the client traffic to a public IP address, depending on which ISP is using it. The FortiGate routing table contains two default routes, one for each ISP. The two default routes are the same distance, but have different priorities. The route with the lowest priority, port 1, is the primary. When both ISP connections are up, the primary route is selected by FortiGate for Internet traffic. So all sessions to the Internet are created using port 1 as the outbound interface. If the administrator increases the priority for port 1 to a value higher than port 2, and if SNAT route change is disabled, all new sessions start using port 2 because it has the lowest priority. However, all the existing sessions continue to use port 1. The default route is through port 1. Even though the default route is no longer the best route, it is still active, and FortiGate is doing SNAT. The existing sessions will continue to use the old route until they expire. If FortiGate wasn't doing SNAT, all the existing sessions would switch to port 2 after the change. The command get router info routing table all displays all the active routes in the routing table. The left column indicates the source for the route. The first number inside the square brackets is the distance, and the second number is the metric. This command doesn't show inactive routes. For example, if you had two static routes to the same destination subnet with different distances, the one with the shortest distance would be active, and the one with the longest distance would be inactive. If you entered this command, it would display only the active route. If you want to display both the active and the inactive routes, use the command get router info routing table database. In the example shown in this slide, the get router info routing table database command shows one inactive route. The route is inactive because it has the longer distance. This low-level command shows the Forward Information Database, FIB, which is the routing information that the kernel uses to route traffic. All active routes in the routing table must be also present in the FIB. Additionally, the FIB may contain routes that are not in the routing table, but were automatically added by FortiGate, such as routes that are dynamically added to reach SSL VPN users. The route cache contains recently used routing entries in a fast-to-search table. It is consulted before the routing table to speed up the routing lookup process. In this section, you will learn about Internet services. The Internet Services Database contains the list of IP addresses, IP protocols, and port numbers used by the most common Internet services, such as Netflix, Dropbox, and Facebook. FortiGate periodically downloads the newest version of this database from FortiGuard. FortiGate uses the information in this database to route traffic to those common Internet services through specific WAN interfaces. You can use Internet services as the destination of a static route. In this example, we are configuring FortiGate to route all the Google DNS traffic through interface port 1. Static routes that you create using Internet services are not added to the routing table. The routes that you create this way are added as policy routes. Also, you can display these policy routes only by using the command diagnose firewall proute list. The GUI does not show these policy routes either. This slide shows the partial output of the policy route created when adding a static route for the Google DNS services. Note that static routes that you create using subnets or named addresses as the destination are added to the routing table. To list the Internet services in the database, use the command get application Internet service status. Each service has a unique ID number, which is used in the command diagnose Internet service ID summary to get summarized information about the port numbers and number of IP ranges associated with the service. To get all the details about an Internet service, use the command diagnose Internet service ID. It displays each and all the IP address ranges, together with the port and IP protocol numbers. The diagnose Internet service info command checks if a tuple IP address, IP protocol, and port number are associated with a well-known Internet service. In the example shown in this slide, we ran the command in the root VDOM to check the IP address 217.89.105.154, IP protocol 6 TCP, and port number 443. The output indicates that the tuple is associated with Google Mail. The following values must match to perform a reverse lookup: VDOM, protocol, port number, and an IP address. Otherwise, you will receive this error: cannot find application ID and name. RET equals -1. In this section, you will learn about WAN link load balancing. WAN link load balancing consists of a group of interfaces connected to multiple ISPs. Once created, FortiGate sees all those Internet interfaces as a single logical interface, the WAN load balancing interface. This simplifies the configuration, because the administrator can configure a single set of routes and firewall policies that are applied to all ISPs. There can only be one WAN load balancing interface for each VDOM. You can configure FortiGate to check the status or health of each interface member. If you configure a detect protocol, a detect server IP address, and a failure threshold, FortiGate will periodically send IP packets to the detect server through each interface member. If the number of consecutive packets that receive no reply for one member goes above the threshold, that member is removed from WAN link load balancing. WAN link load balancing status checks also measure the quality of the links connected to each member. There are 3 different criteria that you can use to measure quality: latency, jitter, or packet loss percentage. You can use priority rules to route traffic based on the link quality of each member. Once WAN link load balancing is enabled, FortiGate starts balancing traffic among all the interface members based on the load balancing method that you select. Priority rules allow you to be more specific about what traffic you want to route through which interface member. You can use priority rules to route traffic through specific interface members, or through the interface with the highest link quality. Remember, status checks are used to measure link quality based on latency, jitter, or packet loss percentage. The priority rules are evaluated in the same way as the firewall policies, from top to bottom, using the first match. The following parameters can be used to match the traffic: source IP address, destination IP address, destination port number, internet service, users and/or user groups, and type of service, TOS. Similar to static routes with internet services as a destination, the priority rules are added as policy routes that can be displayed only from the CLI using the command diagnose firewall proute list. In this example, we have added a rule to route traffic to Google DNS through the interface member port 1. This slide shows the partial output of the added policy route. 2 debug commands display the state and measured link quality of each interface member. The command at the bottom can also be used to find the member ID number of each interface member. The command diagnose sys link monitor VWL status displays some information about the priority rules, such as the mode. The auto mode indicates that the route is selected based on link quality. For those rules using auto mode, the command displays all the members ordered by link quality. The link with the best quality is listed first. The manual mode indicates that FortiGate uses the interface statically configured in the priority rule. The command also displays the ID numbers of the policy routes added by the priority rules. In this lesson, you learned about the following topics: routing table lookup, the route selection process, reverse path forwarding check, return packet forwarding, routing changes and existing sessions, general debug commands, internet services, and WAN link load balancing troubleshooting.